Hello everyone. Today we're going to look at a rather interesting mathematical multiplication called the Mersenne reduction multiplication. My name is Hamoyo. So, firstly, what are Mersenne numbers? Mersenne numbers are numbers of the form 2 to the power k minus 1, where k is in the set of natural, positive numbers. And that essentially means that we can substitute for k over here, say 2, 3, 4, 5, 6, 7, up to some infinity. And these are basically known as Mersenne numbers, and then they are named after a French minimum called Mersenne. And when we resolve this and then the number is prime, then we simply call them Mersenne prime. And the characteristic for Mersenne is that all the bits are set. What do I mean by all the bits are set? So for example, if k is equal to 2, we have 2 to the power 2 minus 1 is equal to 1 base 2. We see that all for each and every example, all the binary bits are 1, meaning they are set. So example 2 to the power 3 minus 1 is 7, which is 111. 2 to the power 4 is 2 to the power 4 minus 1 is 15, which is 1111 base 2. So essentially 2 to the power n minus 1 is n1's base 2. And we see that the first two are prime because 3 and 7 are prime, and 15 is composite. So the third one is, not prime, which is composite. So essentially what we're going to look at is the Mersenne multiplication algorithm, where we have two numbers, a times b mod m. Okay, so we're simply going to multiply a times b together, and then we're going to find the remainder when we divide it by a Mersenne number, which is m equals 2 to the power k minus 1. Okay, so the algorithm is simple. We multiply a and b together, which we store in c, and in c we're going to do c logical end m plus c shift right k, where k is the power of 2 over here. And then when we have the result, we're going to place it into c again, and then if c is greater than or equal to m, we do a subtraction from m, and this subtraction I'm going to term as an extra reduction. Why this algorithm works? So essentially there's the theorem and its proof, and I'm going to simplify it in the next page. So we have a times b, which we are storing in c, and then we're simply going to write c in binary notation. Okay, so we're going to have some c0 plus c1 times 2 plus c2 times 2 to the power 2 up to some cn times 2 to the power n plus 1. Okay, and where these cn, the ck minus 1, c2, c1, 0, c0 are binary numbers, which is 0, 1. Okay, and so I'm going to split c into lower bits and upper bits, or higher bits. So the lower bits, essentially, I'm going to write from this point, which is c0, up to the very last value before this. Okay, so the last value is going to be ck minus 2 to the power k minus 1. Okay, so that's going to be our lower bits, and the upper bits is essentially this to the end. Okay, so that's essentially what I've written here. Okay, now what I'm going to do with the higher bit is that I'm going to factorize the power of 2 to the power k out, and if I factorize it out, I have this. That is to say that if I multiply this and this, I'm going to have this. Then if I multiply this and this by this, I'm going to have this. Okay, so it's nothing new. So for the higher bits, we see that I have simply factorized out 2 to the power k. Okay, but one interesting property about the Mersenne numbers is that when we are doing a modulo operation, okay, where we have 2 to the power k, it's always going to be congruent to 1 mod the Mersenne number. What I mean is this. So for example, if we have k to be, let's say, 3, we have 2 to the power 3, which is 8, is going to be congruent to 1 mod 7, where if k over here is 3, we're going to have 8 minus 1, which is 7. So what's the remainder when we divide 8 by 7? It's going to be 1. Likewise, when k is equal to 4, we're still going to have the remainder to be 1, and so on and so forth. So essentially, if we apply the modulo operation with respect to the Mersenne number on this line, essentially the 2k becomes 1, so it vanishes. So we have the following relation. Okay, and how do we extract the lower bits computationally? So to extract the lower bits computationally, we're just going to do C logical end with M, and then for the higher bits, we're just going to do C right shift K, okay? And then if we do an extra reduction if needed, okay? That is if C is greater than or equal to M. So this is what I mean, essentially. So let's say M is equal to 31, and then C is equal to 1,000. We know 31 is a Mersenne number because 2 to the power 5 is 32, minus 1 is 31, okay? And C is 1,000. We just write C in binary notation, okay? So this is essentially the same thing, C in binary notation. Then in the previous slide, we saw that we're going to have to do C logical end with the modulus, okay? So we know our modulus to be 1, 1, 1, 1, 1. So we're just going to be doing C logical end with the modulus. Essentially, we are just appending zeros in front of the modulus, okay? So logical end, remember the truth table, we're simply going to do 1 and 0, which is 0, 1 and 0, which is 0, or as some people call it, true and false, true and false. And here we have true and true, we have 1 and false and true, so on and so forth. And we see that we extract the lower bits of C. Okay, so this should match this. And then for the higher bits, we're just going to do a right shift. So this is C, we are doing a right shift of 5. So that means we're going to take 5 out. So we have 1, 2, 3, 4, 5. When we take these ones out, the remainder is what we have here, which is 1, 1, 1, 1, 1. Okay, I suppose, yeah, 5 of them. So essentially what we're going to do is we're going to convert this 1, 1, 1, 1, which is the upper bits, back to our decimal notation, which is 31. And we're going to take the lower bits, which is this one, which is essentially 8. And then we're going to add them. Okay, so we have 8 plus 31, which is equal to 39. But we see that 39 is still greater than our modulus, so we're just going to do 39 minus, essentially we're doing 39 minus 31. Okay, so we have our results to be 8. Okay, so this algorithm in itself it doesn't really have an inventor behind it. It just came about through numeric theoretic properties of Mersenne numbers. Okay, I find it really fascinating because it appears a lot in cryptography, especially in computer algebra, and also like pseudo number random generators and all that. So essentially, let's just look at how it's done in C and Nasm. So in C, we see that we have our main function here, and in the main function, essentially, we're just going to check the number of arguments, okay, because we're going to run it this way, okay, our program A, B, and K, and because we're going to have 1, 2, 3, 4, so we're just going to check if our number of arguments is 4, okay, because we have the program name A, B, and K, so 4 of them. And if it's not, we're just going to print out an error message and then return 1. Otherwise, we're going to have to convert A, B, and K into integers, because when you pass them in, they're actually characters, not integers, okay? So we're going to have to convert them to integers using the A2I or ATOA function. Then we're going to call upon our Mersenne compute function over here, which we've already looked at. Basically, the algorithm is the same as follows. So we have A times B, the modulus is 2 to the power K minus 1. And then we do the C logical end with modulus plus C right shift K. And then we do an extra reduction if needed and then return C. Then lastly, this last routine over here is just printing the number back out to screen. Because the number is an integer, we need to, place it into a buffer called the output and then write it back to the screen. This much we've already seen, okay? So let me just try running this. And then we see that if A is equal to 20, B is equal to 50, we multiply them together, we have 1,000, and then 5, because 2 to the power 5 minus 1 is 31. So essentially we're doing 1,000 modulo 31. Okay, so our answer should be 8, okay? So let's just go back and look at our C code. So essentially this one I want to show you guys. Now let's look at our Nasm. In our Nasm code, of course, because let's start from the start. RSP over here, we know that contains the number of arguments, so essentially congruent to this part of the C code. And so we're just going to place that into the R8 register, and then we're going to check the R8 register whether it's equal to 4. If it's not equal to 4, we print out our error message, which is essentially this one, Okay, so this print and exit one are basically like macros I've already written in this one. Okay, I included a macro. We've already looked at this. Then also, if it's equal to 4, we're going to have to convert the parameters into integers, just like in the C. So we have the A, B, K. We're going to convert them into integers, this part. And we've already seen that A is basically RSP plus 16, B is 24, and K is going to be 32. The difference are always going to be of 8, okay? And we've already seen that when we're passing arguments into a function, or like a C function, the first argument always goes to RDI, and because Atwa only needs one argument, we're going to have to pass in our values into RDI. Then our results is going to be placed into the RAX register, and then I'm going to place the results into the R12 register, which is a non-volatile register. We've already seen this in the functions non-volatile and volatile registers, or caller and callee saved registers. The same applies for the B. I pass it into the RDI, I call Atwa, and then the results is going to be placed into the RAX, so I pass it back into R13, and then for the K, I pass it into the R14. So basically R12, R13, and R14 are going to receive A, B, and K respectively. And so because I'm going to call another function which is called the Mersenne compute, as we've already seen, I have to repass them the values again into their corresponding, arguments, or function registers. So A is going to go into the RDI because that's our first function argument. Then B goes into the RSI, then C, the K goes into the RDX. Okay, so accordingly, then we call our function using the call. Okay, so up here we have our function. Okay, so we start with the directed Mersenne compute, and because our return value is C, so I'm just going to use RAX to hold the C value, which is our return value. So RDI contains A, so I'm going to pass A into the RAX, which so essentially we're going to say C equals A, and then I'm going to multiply the value of B with the value of C. The A. So we have C is equal to AB. So essentially what we're doing here in these two lines is just basically the C part, which is C equals A times B. Then I'm going to have to pass in the DL. The DL is basically the lower 8-bit register for the RDX, okay? Remember, K is passed into the RDX. I'm just calling the lower bits of it, or the lower 8 bits of it. So the lower 8 bits, I'm just going to place it into the CL, where the CL is also the lower 8-bit register for the RCX register, okay? And then this part, I'm going to pass in the value of C to RDI, okay? And then RDI, I'm just going to say we're going to shift right CL, okay? Essentially what that's doing over is basically this one. So we're doing C right shift K, okay? And why did I need to move the DL into the CL? Because of the shift right operation, it only takes the C and RCX register or the CL register, okay? So that's why I had to use the CL. I tried using the DL, but it didn't work. So yeah, you have to use the RCX register. And so we have the C shift right K. Then also over here, basically we're going to do this part where we're just computing the modulus from the K. So pass 1 into the RSI. I do 2 to the power K, which is a shift left, and I decrement by 1. So we have 2 to the K minus 1. So essentially RSI is going to hold the modulus. Then I'm going to do C and the modulus, which is essentially this part. Okay, so I do C and the modulus. I have the results, and I'm going to add it to, this one we've already looked at, which is the RDI. I'm going to add it to the RDI register, and then basically the results is going to be placed back into the RAX register. So we enter our loop, and then we check whether the RAX, we check the RAX against the RSI, which is essentially C against the modulus. And if it's less than, we exit the loop. Otherwise, we subtract, which is the extra reduction over here. And always remember to add the RET, which tells the instruction pointer where in the code to return to. So essentially, after calling our function, RAX is going to place the result into a variable I've named perfectly as results. I stored it here. Okay, so I have the results here, which is a 64-bit integer. Then at the end, I'm just basically going to print it back to the screen. So we have this and this and this. So essentially, we pass it into a buffer and write it onto the screen. Then we print a new line and then we exit gracefully. Okay, so this print num and print and then the exit are basically macros in the include my macros.inc. And always please don't forget to add the extend a2i at the very top, so it knows that it's a C function it's calling for. So let me save this. Let's try to run this, and we see that 2055 should basically give us our value 8. So this is essentially what I wanted to show you guys today. If you like my video, please like and subscribe to it, and thank you all very much. Bye.